Good afternoon to those of you who are in Europe, and a very warm welcome from Lausanne to this new installment of the CCAM Mixed Gen online webinar series. So as all of you have seen, today we have an interesting program based on the simulation and modeling of electrochemical interfaces and capacitors. Our experienced speaker from the day is Benjamin Rothenberg from CNRS and Sorbonne Université. And then we have two, in principle, junior speakers' contribution, although we're still waiting for one of them to connect. We'll see how that goes. Just a quick reminder, the reason why we started this series was to facilitate networking and communications, in particular for early career researchers or in general junior members of our community, at a time when COVID made it impossible to meet in person in schools and workshops and conferences. Now we're returning slowly to some kind of more normal type of interactions, but the feedback that we have got for this series convinced us that it's not a bad idea to keep going for a while, also to provide people who cannot travel that easily, who may be busy in their schedules, to actually have a broad perspective of the field through this series of lectures that we have. My name is Sara Bonella. I am the Deputy Director here at CCAM, and it's going to be my pleasure and my duty to moderate today's session. In order to do that, let's start. I will screen share in a rather basic fashion, just to share with you some basic information. First of all our mixed gen sessions are recorded, so be aware of that. We do encourage as much interaction as possible with our speakers. However, for this particular series, we do this by using only the Q&A tool of Zoom as a first interface between us and the participants. The first talk, which is going to be a bit longer than the others, is one in which Benjamin will introduce the field and explain recent developments. If you have questions that you feel you would like to ask our speaker during this talk, please do that. I will relay those questions that you will have written in the Q&A tool directly to Benjamin. And this is going to be the modus operandi during the talk. At the end of the talk, you should just signal that you would like to ask a question by typing it in the Q&A, and then you will be invited to unmute your microphone. No camera activation, but you will be able to unmute your microphone so you can ask your question directly and then interact with Benjamin with follow-ups if that's necessary. For the two talks by our younger guests today, I mean, Benjamin is ridiculously young, so that feels a little strange as a sentence, but for Moui and Geoffrey, the way we're going to play it is that all questions will be answered at the end of the talk. So you will be asked to just unmute yourself after signaling that you do want to ask a question in the process. Now, there's one thing that I wanted to point out, which is that you can find information about this series and all activities of CCAM going to our website. For those of you who do not know it yet, this is the CCAM.org website. And if you navigate it through the main page, for example, here you will have a complete list of our events, both online and in person. And if you follow the link to the Mixed Gen, oops, that's not what I wanted to do. If you follow the link to the Mixed Gen session here, you can find details on what is going to happen today and how to participate. And if you're interested in the future, how to submit posters. Now, another thing that you can do if you want to receive regular information about our activities, the Mixed Gen, or our or other online activities such as the CCAM Marble Classics or the CCAM Marble Marianne Menside Conversations, is you can, if you haven't done that already, but register to the CCAM mailing list by clicking on this tab and then following instructions. So this is really all I wanted to say. As always, let me encourage all of you to be as interactive and participative as possible, both as participants and among our panelists here. And with that, without further ado, I would like to give the floor to Benjamin, who will discuss for us electrode and electrolyte interfaces from electronic response to interfacial structure, dynamics, and thermodynamics using classical molecular simulation. So Benjamin, the floor is yours. Thank you.
Thank you very much, Sarah, for the introduction and also for the kind invitation. I hope you can see my screen.
Everything seems to be working fine.
Perfect. So thank you all for joining today. Thank you if you're also visiting to watch the replay. I will tell you about some work we did over the past 12 or even 15 years in the Phoenix lab in Paris. So the Phoenix lab is a physical chemistry lab shared between CNRS and Sorbonne Université. And its work related to electrode-electrolyte interfaces, and specifically what classical molecular dynamics simulations can bring to the understanding of the interfacial structure, dynamics, and thermodynamics of these electrode-electrolyte interfaces. And in order to do that, we need to incorporate in the classical MD simulations some elements, some features of the electronic response of the metal to the presence of the electrolyte. So I'd like to present you how these things work and give you some examples of what we can learn using these classical MD simulations. Before I introduce the broader context of metal electrolyte interfaces, I'd like to thank a few people who have been involved in that work over the years. And I've highlighted a few people, in particular, my colleague Mathieu Salan in Paris, who's really been involved in all the work I'm going to present, and who's also the main developer of the Meta Walls code, which I'm going to mention later on, which is the classical MD engines that we're using, and he's the main developer of that code. The work started a while ago in collaboration with the experimental group of Patrice Simon, who's working on supercapacitors, and I'm going to tell you about supercapacitors in a while, and especially during the PhD thesis of Céline Merlet. So I'm also going to refer to earlier work to set the stage. But I'm going to focus more on recent work, especially from the PhD of Laura Scalfi, who was a former PhD student in our group, and the ongoing postdoc of Giovanni Pireddu. So I'll tell you more about that. And finally, many of the things I'm going to tell you about were done in a long-lasting collaboration with David Limmer in Berkeley University. Okay, so where do we find metal-liquid interfaces? You can think of rather basic applications where you use a liquid to reduce the friction between two metal pieces, so lubrication. And of course, the details of the friction depends on the interactions between the liquids and the walls. I'm not going to say a lot about that today, but I'll come back to this issue at the very end because there are very interesting physical chemistry questions associated with the friction at liquid metal interfaces. You can also use the fact that metals respond to voltage, and charges in general response to electric fields to tune the interfacial properties involving metals. So this is an example of work in the group of Alexei Kornichev, who used a voltage drop across an interface between two liquids, an aqueous electrolyte and an organic electrolyte, to drive gold nanoparticles to the surface or away from the surface using voltage in order to change the affinity of the gold nanoparticles for the surface. And this allows to assembling these nanoparticles at the surface to form a nanoplasmonic mirror at this liquid-liquid interface. Now, of course, electrodes can act like electron reservoirs to perform reactions at the surface. So this is the field of electrocatalysis. I'm not going to say too much about that, but this is a huge field and very important one, and also very interesting from the fundamental point of view. I'm going to tell you more about things that are related to sensing applications, so electrochemical sensing, where you use electrodes in microfluidic or nanofluidic devices in order to detect the presence of charged species or redox active species. You can measure the current or the charge of the electrode and look at the fluctuations of the charge or the currents in order to infer information on what happens at the interface between the solution and the electrode. And of course, the main application you probably have in mind for electrode-electrolyte interfaces is energy storage. And I will not talk about batteries, but rather capacitors and devices called supercapacitors. So in both devices, you have two conducting plates. And in a conventional capacitor, these plates are separated by the electric medium. And the charge and the plates, if you apply a voltage, so potential difference delta psi between them, you will accumulate opposite charges on the two plates. And the charge over the electrode is proportional to the voltage, and the proportionality constant defines the capacitance. Here, C, in fact, it's called the integral capacitance because it's a ratio between the charge accumulated and voltage. The energy you can store is quadratic in the voltage. It also involves the capacitance. And the capacitance can be defined either as the integral capacitance, as I've just mentioned, or as the differential capacitance, which is the derivative of the charge on the electrode with respect to voltage. And in the case of the capacitor, standard capacitor, both the integral and differential capacitance coincide, and they are equal to this quantity here, which is the product between the permittivity of the dielectric medium, the area of the conducting plates, and it's inversely proportional, the capacitance, to the distance between the two electrodes. The principle of the supercapacitors or electrochemical double layer capacitors is very similar. You also have two electrodes, but now they are separated by a liquid which contains mobile ions, so an electrolyte or an ionic liquid. And the charge of the electrodes is not balanced by the polarization of the dielectric medium as previously, but it's the charge is compensated by an excess of counter ion and a depletion of co-ions near the surface. And of course, there is the opposite excess and depletion on the other side. So in contrast to batteries, there is no redox reaction at the interface. So the charge is accumulated by the absorption of ions. And in order to increase the capacitance of the system, you want to increase the contact area between the liquid and the solid. And so you typically use carbons with high surface area. As I've already mentioned, the electrolyte is either an electrolyte solution or a dilute or concentrated, or even more complex liquids, which consist only of ions, called ionic liquids, which are like a molten salt, but liquid at room temperature. So these supercapacitors are already used in real life. So in order to illustrate where they stand in terms of energy storage devices compared to batteries and conventional capacitors, it's usual to plot this kind of diagram where you report the devices in terms of the specific energy, so how much energy you can store per mass of material, and specific power, which is the power you can deliver per mass of your material. And here with the high specific energy and low specific power, you have the batteries, whereas on the top left, you have capacitors, which can deliver a large power but store little energy. And the electrochemical double layer capacitors are somewhere in between. So they have a relatively high power compared to batteries and relatively high energy compared to standard capacitors. And also what is important to notice is that they can be charged or discharged within seconds. And they have a long cycle life, which means that you can charge and discharge them many times before the performance starts to deteriorate. So they are used in specific applications where you need a high power, so fast charge and discharge. And for example, you can use them to recover kinetic potential energy. So here you have an example of a tram in Paris. And whenever the tram breaks, instead of dissipating the energy, the kinetic energy as heat, you can charge some supercapacitors and reuse part of the energy that would have been lost when you start moving again. And here is the same game with a harbor crane. So you recover potential energy when the crane goes down. You can use that to charge supercapacitors and then use that energy that was stored when you lift the crane again. It's also used in a hybrid electric vehicle, for example, for the start-stop system or as a booster, and also for electric drive. So instead of using batteries, you can use supercapacitors, but because you cannot store a lot of energy, it's limited to specific applications where you have frequent stops and you can charge again during the stop. So here is an example with a small boat that travels short distances, and here a bus that only travels short distances between two stops and can charge fast during the stops. Another application that is less standard and but I think quite exciting is also the possibility to use capacitors to harvest blue energy or to desalinate water. And there is a process called capacitive mixing, which was proposed in 2009 by Progioli in order to extract the mixing-free energy that is lost when salty water and fresh water mix. That's the case, for example, when river water goes into the ocean. There is a lot of free energy which corresponds to the mixing free energy that is dissipated, and there have been various attempts to extract that mixing free energy. One of them is capacitive mixing, which involves cycles where you charge and discharge the electrodes and change the electrolyte between them during the charge and discharge. I'm not going to describe the cycle at length, but the idea is that during part of the cycle you will spend some energy, during other parts of the cycle you will recover some energy, and the overall cycle allows you to extract some energy. So it's the same as in a thermal engine. Sometimes you spend, sometimes you recover energy, and there is a net balance, which is that you gain some energy during that process. You can do the reverse process and spend energy to desalinate water using what is called capacitive deionization. So I'm now going to go more into the details of these electrode-electrolyte interfaces, and this slide is just to illustrate the variety of interfaces that have already been simulated using classical MD simulations. Here are some examples with ions at the platinum water interface, looking at the influence of the interface on the dynamics of pair formation and dissociation. By David Limmer and Adam Wheeler. Here is an example by Simone Pezzotti and co-workers where they looked at the absorption of hydrophobes at the gold-water interface. And here are two examples related to energy storage with different liquids. So here is an earlier example with graphite electrodes and butyl methyl imidazolium hexafluorophosphate ionic liquid using a coarse grain model. I'm going to show you some results with this coarse grain model of this ionic liquid. And another example more recent with another type of electrolytes, which are called water and salt electrolytes, where you have as much ions as water. So you can mix water and these kind of ions in very large amounts. And this leads to a change in the electrochemical response of water compared to aqueous solutions, which may be useful for battery applications. I'm not going to discuss that in detail today, but I should mention from the beginning that electrodes are not always flat. And in fact, in many applications for supercapacitors or blue energy harvesting and desalination, the porosity of electrodes plays a very important role. And in the past, we've looked at nanoporous electrodes in these two contexts. And there, the fact that you have pores that can have various shapes, but have a size comparable to the size of the ions plays a very important role. And so many features related to the charging process are in fact related to the porosity, the nanoporosity. I'm not going to discuss that today because it would be a completely different talk. It could be a topic for another mixed gen series. But if you're interested, you can have a look at these review articles that we wrote last year. Another important point that I'm going to discuss in the second part of the talk is the fact that electrodes are not always perfect metals. And I'm illustrating this here with an experimental study in the group of Lideric Bocquet in Paris, where they investigated the capillary freezing of ionic liquids, which is related to interfacial thermodynamics, by using the tip of an AFM to probe the response of an ionic liquid on a substrate. And so when you confine the liquid between the tip of the AFM and the substrate, there is at some point a change in the mechanical response from liquid-like to solid-like. And this change in the response occurs at a particular distance here, lambda s, which depends a lot on the nature of the substrate. And they could rationalize all their observations by describing the length at which capillary freezing occurs by characterizing the substrate with the screening length within the substrate. So the Thomas Fermi screening length, which is the inverse of this KTF here. I'll get back to the screening length later in my talk. And even though these surfaces, the mica, graphite, the silicon or platinum, differ by other features, they could rationalize the result as a function of the screening lengths, and showed the importance of screening lengths on the interfacial thermodynamics, which leads to the capillary freezing of the confined ionic liquid. So I'm now going to switch to the modeling of electrode-electrolyte interfaces, and I will start from the standard picture which follows from continuous descriptions, and the general picture of electrode-electrolyte interfaces and charge interfaces in general is that of an electric double layer, where the solid surface carries a charge and the liquid next to it carries an opposite charge, which is diffuse, and it results from the balance between electrostatic interactions and the entropic benefit of being in the liquid phase. And the standard theory for the description of such electric double layers is called Poisson-Boltzmann theory, which captures both electrostatic and entropic components. If you linearize Poisson-Boltzmann theory, you get the Debye-Huckel theory, which is maybe more familiar to some of you. And this Poisson-Boltzmann or the Debye-Huckel theory makes a number of assumptions to describe the system. For example, you consider point-like ions in an implicit solvent characterized by its permittivity. You use a mean-field description of electrostatics. Usually you consider a smooth surface, a perfect metal, even though you can also introduce a screening length at this level of theory. And if you do that, you predict that the potential or the density, ionic density profiles decay as a function of the position, so the distance with respect to the interface. The decay is exponential in the Debye-Huckel theory. You have an excess of counter-ions, of course, and a depletion of co-ions. And the exponential decay occurs over a characteristic distance, which is called the Debye screening length here, lambda d, which depends on the permittivity of the solvent, the temperature, the ionic concentration, and the valence of the ions. And the capacitance associated with the potential drop at the interface is similar to what we had previously for a conventional capacitor with the permittivity in the area, but now the relevant distance is not the distance between the electrodes, but really the Debye screening length. Now, some of these assumptions that I've just mentioned can be relaxed using, for example, classical density functional theory. There are many things that can be captured at a continuous level or using classical DFT, especially the finite volume of the ions and correlations beyond the mean-field theory. You can look at the works of Kornichev or Van Hooy, for example. But what I would like to, this would be again a completely different talk. What I would like to emphasize today are the contribution of molecular descriptions to the understanding of these interfaces and looking at the structural, dynamical, and thermodynamical properties. Before I switch to what we actually do in the group, because of course I will focus on the kind of things we do in the group, I should emphasize that it's a very active field of research. There are many groups that have developed over the years various approaches, both in classical and ab initio molecular simulations or DFT calculations. I'm not going to describe everything in detail. I've just highlighted a few important references. If you're interested, just watch the replay and you can pause and look at all these very interesting references. Please don't be offended if you don't find your own work or your favorite methods in this slide. It's just a sample of the methods that are used to illustrate that this is really a very active field of research. So as I've mentioned already in the title of this talk, I'm going to focus on classical molecular simulations. The reason why we want to use classical MD is that for the systems I've mentioned, so especially the nanoporous carbon electrodes, even though I'm not describing that in detail, but also for things like phase transitions and double layers that may extend over several nanometers, you easily need thousands or up to 10 or 100,000 of atoms, and the processes that you need to simulate, the simulation times you need to explore are of the order of several nanoseconds to tens or hundreds of nanoseconds. And so this is usually not easily achieved with ab initio molecular dynamics. So this is why you need a simplified description with classical MD simulations. And you need to sample the configurations of the electrolyte that correspond to the constraints that the system that you are considering has to satisfy. So for example, you want a constant temperature as usual when you're trying to model a system, an experimental system. It's usually not a fixed energy, but a fixed temperature. But you also want to describe a metallic surface which may accumulate charge due to the presence of voltage and of the electrolyte. So what is actually fixed is not the total charge of the electrode, but rather the potential of the electrode. And even though it's quite subtle, you also need to impose the constraint of global electroneutrality. As I've mentioned also in the title of this presentation, you still need to include in this classical description some features of the electronic response of the metal, and there are several ways to do that. Here is a figure from a recent review, if you're interested. And all these methods are used in various contexts to do MD simulations, for example, based on the continuum picture of image charges at the planar interface, where everything that happens on the liquid side with the charges of the ions or the partial charges of the solvent molecules. So from the electrostatic point of view, you can predict what happens in the liquid on the liquid side by assuming that you have image charges on the solid side, which with a magnitude that depends on the two permittivities inside and outside the solid. And so if you're doing MD simulations, you can compute interactions in the liquids by modifying the energy, the electrostatic energy calculation and the force calculation by introducing the presence of these image charges. You can also use Poisson solvers to determine the charge induced at the surface of the metal. So this is an example from work in Christian Holm's group, where the charge on each surface element is computed to satisfy the correct boundary conditions at the interface. Here is another example of how to deal with electronic response, or at least the charge distribution, how it responds to an external charge. Here, a sodium atom next to a gold electrode. You can do that by introducing a core shell model which is represented here. And what I'm going to tell you about in more detail is another method where the charge of the electrode responds to the presence of the electrolyte, not by moving shells, but rather by changing the magnitude of the charge on each electrode atom. So it's a fluctuating charge model, which I will describe in more detail. But before I do that, let me just quickly motivate the need to use this constant potential setup, or at least taking into account the electronic response. In early studies of supercapacitors, people used to model the interface, the solid side of the interface with a constant charge, assigning a constant charge to the electrode atoms. And in that work during Céline's PhD, Céline Marais' PhD, we showed that in fact it can be quite dangerous to do so. So for the structural properties of the interface, you can see differences, but the most dramatic effect is probably on the dynamics. So here is an excerpt from the abstract, but I've highlighted two examples related to the dynamics. So if we look at a single electrode during the charging process for an unopposed carbon electrode, at time 0, we can apply voltage between the two electrodes. And if you wait for a few picoseconds, well, ions are moving, but they still haven't really filled the rightmost part of the electrode. Whereas if you instead start from the same configuration and assign to all electrode atoms the average charge that the electrode atoms will eventually get if you wait long enough at the same voltage, then within a few picoseconds, all the pores are filled, the ions have been driven by a very large field. And in fact, it's way too fast. So if you look at the temperature increase as a function of time during the charging process, without a thermostat, because otherwise the temperature would be constant. So the temperature increases slightly for a relatively small voltage. If you multiply the voltage by 5, then the slope, so the power that you inject is multiplied by a factor 25, as you would expect from the Joule heating process, so you're using Ohm's law. And in fact, if you do the constant charge process, then within a few picoseconds, you reach completely unphysical temperatures. So it's really important to use this more expensive, but physically more relevant way of dealing with the electrons. So how does that work, this constant potential fluctuating charge method? So in this model, the electrode charge distribution is modeled as a sum of atomic contributions, and each atom carries a Gaussian charge distribution at the position Ri of the electrode atom with a Gaussian width sigma, which is fixed. But the magnitude of the charge fluctuates, so Qi fluctuates in order to enforce the fixed potential and global electroneutrality conditions. So you have usually a setup like this with two electrodes. You have one value for the potential of all electrode atoms on each electrode, and you apply voltage by considering different values for the two electrodes. And this process was first proposed by Sipman and Sprick, who looked at water under the tip of an AFM, and it was using Carparinello dynamics for the fluctuating charges. And then in Paul Madden's group, they applied the same model of electrodes with electrochemical setup and using a Born-Oppenheimer sampling of the charges. The total charge density is the sum of the electrode charge distribution and that of the electrolyte, which usually contains point charges, but it can also contain dipoles. And then the electrostatic energy is written like this. And you can notice from this expression that it is quadratic in the partial charges, which will play an important role. And the electrostatic energy requires computing the interactions between point and Gaussian charge distributions, also dipoles if you have dipoles in the electrolyte, and also taking into account the fact that you usually have 2D periodic boundary conditions in an electrochemical setup. There are ways to deal with this by doing a computation in 3D and then correcting for the third dimension, but I'm not going to discuss the details of that today. So the total energy can be written like this. You have a first term that contains all non-electrostatic interactions and the electrolyte-electrolyte interactions. Then a term which is quadratic in the charges, which contains all the electrostatic interactions. So Q here is a vector which contains all the individual charges of electrode atoms, and A0 is a matrix that depends only on the position of the electrode atoms and the Gaussian widths of the charge distribution around each atom. And you have a last term which captures the Coulomb interactions between the electrode and the electrolyte. So it depends on the configuration of the electrolyte. And once you have this expression of the total energy, you can do a Born-Oppenheimer sampling of the charges. For each electrolyte configuration, you need to find the charges that satisfy the constraints of fixed potential on each electrode atom. So the vector psi here contains the list of all prescribed value for the potential. So typically it's one value for each electrode, as mentioned earlier. And then you can determine the charges, the Born-Oppenheimer charges, by doing the matrix vector product. So the matrix here contains the inverse of the A0 matrix, which comes from the total energy. And it contains, there is another term here which only depends on this matrix. So E is a vector which contains only one in each entry. So you can compute this matrix one and for all, and then just multiply this matrix by the vector which depends on the electrolyte configuration plus the potential, the vector of potentials. So in practice, you can do this inversion once and for all if the system is not too big. If it's difficult to do the inversion, then you can formulate this as a minimization problem and use conjugate gradients, or use another algorithm that was proposed recently, which allows you to modify the dynamics to stay on the hyper plane of the phase space that satisfies all the constraints. I'm not going to describe that in detail. So what is also important is to understand what we are actually sampling when we do this Born-Oppenheimer dynamics on the charges. And we wrote explicitly the statistical mechanics of this constant potential ensemble. In particular, what you need to start from the partition function, which involves the degrees of freedom, which in principle involve the positions of the electrolyte atoms, but also the charges, the fluctuating charges of the electrodes. Then the weight of each microscopic configuration depends on the configuration, the charge, but also the set of potentials that define your constant ensemble, constant potential ensemble. And finally, you need to introduce electron neutrality constraint. So again, this E vector is just with ones. And so if you take the scalar product with the charges, it will give you the sum of all charges present in your system. So you can write the partition function. From that, you get the free energy. You can compute the probability of a configuration of an observable and so on. And for example, we worked out a fluctuation dissipation relation for the capacitance, which tells you that the response of the charge to voltage, the differential capacitance, is in fact given by the variance of the charge distribution. So Q here is the total charge of one electrode, and the charge of the other electrode is simply minus Q. And so this variance of the charge distribution divided by the thermal energy KBT, which is a beta factor here, gives you a way to measure the differential capacitance. Now, there are also subtleties related to the Born-Oppenheimer sampling. For example, the average charge of the electrode is correctly sampled with this scheme, but the differential capacitance includes the variance that you measure with the Born-Oppenheimer charges, but also another term which escaped our attention a few years ago, which in fact depends only on the configuration of the electrode atoms with this matrix A0 and also the width of the Gaussian distribution around each atom. And it in fact corresponds to the differential capacitance for an empty capacitor, which has its own capacitance even when there is no electrolyte between the electrodes. So let me now show you some results. So for example, in this earlier study, we considered two different capacitors. So here is an illustration where you have different electrodes, but in fact, each system has two identical electrodes just to visualize how they look like. So the first system is an electrolyte with butyl methyl imidazolium hexafluorophosphate in acetonitrile using a coarse grain model that you see here. So this is the first layer of adsorbed liquid at the interface with a graphite electrode. And the other system we considered in that study was pure water between platinum electrodes. And you see here, again, the configurations of water molecules in the first adsorbed layer. We sampled the total charge distribution. So this is a probability to observe in equilibrium a given charge Q of the electrode. And it's normalized here by the variance of that distribution. And you see that in both cases, the distribution is very Gaussian. And this implies a linear response of the charge, the average charge as a function of voltage, which is what we observed as the symbols during simulations at different voltages. And the lines here are lines with the slope predicted from the variance of the charge distribution. So you see that there is a good agreement with this prediction, even though at that time we had missed the contribution of the empty capacitor. And the reason why we didn't notice is that it's very small, which you can see here. So here is another system for a more recent study. I'll get back to this system later on. So it's pure water between model gold electrodes for various distances d between the electrodes. And what you see here is the differential capacitance. So in red and blue computed from the fluctuation dissipation formula. The red part is the Born-Oppenheimer contribution, and the blue part is the empty capacitor contribution, which you see is rather small. If you compare the total differential capacitance to the prediction from continuum electrostatics, which is the red line here, so the permittivity of water, bulk water divided by the distance, you see that there is a trend, which is that capacitance decreases as you increase the distance between the plates, but it's quantitatively quite wrong. And the reason is that, in fact, this continuous prediction neglects what happens at the interface. And at the interface, the liquid is quite structured, and the potential drop at the interface is not well captured by the continuous prediction. And one way to link the continuum picture with the microscopic potential drop at the interface is to introduce what Roland Netz and his coworkers introduced, which is called the dielectric dividing surface. So for those of you who know about adsorption, there is a way to partition an interface between two homogeneous regions, which is called the Gibbs dividing surface. So here it's very similar, but for the permittivity. So you can measure the local permittivity, or at least one component of the permittivity tensor, looking at the polarization fluctuation. And then from this permittivity profile, you can define the position of the DDS, the electric dividing surface. And this, from using this position, you can look at the permittivity, an equivalent permittivity profile, which would be one for the vacuum region next to the interface, and then the bulk permittivity water between the two DDS, so one on each surface, which defines an effective width of the capacitor, DDS. And here is a prediction of these capacitors in series model. So the black symbols, and you see that it's a much better prediction of the differential capacitance obtained from simulation using this simple model, so a coarse-grained description of the interface. But the charge fluctuations of the electrodes are in fact related to what happens at the interface. So we can use these charge fluctuations as a source of information on the electrolyte configurations or the observables associated with electrolyte configurations. And if you again come back to the statistical mechanics of the constant potential ensemble, you can look at the probability of each microscopic configuration or of a given observable A, for example, the number of adsorbed ions, molecular orientation, structure factors, and so on. So here, for example, you see that the charge below a water molecule depends a lot on its orientation. Here, it's pointing with an OH bond pointing towards the surface, and the local charge of the electrode atom is negative, whereas here, where you have a molecule lying flat on the surface because it's making hydrogen bonds with neighbors, then the electrode atom below the oxygen is locally positively charged. Yes?
Sorry, just as per your request, we have reached the 40 minutes mark. I'm not sure that we always see your pointer on the...
Oh,
so
thanks
just pay
for
attention to that.
letting me know. Is it better like this?
Yes, thank you.
Okay, sorry about that. And thanks for the notice. And so coming back to the statistical mechanics of the constant potential ensemble, we showed that there is a way to optimally predict the evolution of any observable as a function of voltage continuously by doing several simulations at a few voltages by sampling the joint distribution of the charge, electrode charge, and the observable. And I'm going to illustrate that using the case of a capacitor consisting of graphite electrodes with a room temperature ionic liquid. So here you see the setup, the coarse-grained model on the left, and the electrode charge distribution for a single configuration with also the configuration of the ions in the first adsorbed layer. So the right figure here shows you that there are indeed definite layers. So these are density profiles for the anions in green and cations in red. There are definite layers next to the surface. And what you don't see in this 1D profile is that there are lateral correlations, which we can measure and quantify using the in-plane structure factor and do this as a function of voltage. I'm not going to show you the structure factors, but the surface charge density, so it's just the total charge Q divided by the lateral area. Here plotted as a distribution, so the red region is a high probability, blue region a low probability as a function of voltage, which we reconstructed using these reweighting techniques. You see that it's not linear anymore. The distribution, if you look at cuts for a given voltage, here are a few examples, they are not Gaussian anymore, and this non-Gaussian distribution is reflected in a nonlinear response of the charge. And if you look at the differential capacitance, which we compute using this fluctuation relation, then the differential capacitance evolves as a function of voltage, so in contrast to standard capacitors. And for example, this peak in the differential capacitance, we could associate with an order-disorder transition in the first adsorbed layer in the ionic liquid. We've recently extended this fluctuation dissipation relation to the frequency-dependent response. So the linear response of the current, which is a time derivative of the charge to a small oscillatory voltage, is usually quantified by the admittance or the impedance. So if you have a small oscillatory voltage at a given frequency omega and measure the current at the same frequency, then the linear response is quantified by the complex admittance or its inverse, the complex impedance. And you are probably familiar with the impedance of a resistor, which is simply the resistance, the capacitor, which is 1 over I omega times the capacitance, or for an inductor. And this kind of measurement, it's routinely used to characterize electrochemical devices. So for low frequencies, you can use electrochemical impedance spectroscopy, or at higher frequencies, this corresponds to dielectric spectroscopy, which people try to relate to microscopic mechanisms. For example, ion pair formation and dissociation, the ion cloud relaxation, molecular reorientation, H bond defects, reorganization, and so on. And so the extension of the fluctuation dissipation relation that you've seen before for the differential capacitance looks as follows. So the admittance is the sum of two terms which are related to the variance of the charge distribution as before. And in fact, this is just I omega times the differential capacitance, if you have the beta factor here. And another term which is related to the Laplace transform of the charge autocorrelation function. So the admittance is directly related to the dynamics of the equilibrium charge fluctuations. And here are some examples for the charge autocorrelation function for this water gold electrode capacitor for various distances. I'm not going to discuss that in detail. We could also link these charge fluctuations to the dipole fluctuation of the liquids. And in fact, the charge fluctuation is directly related to the perpendicular component of the dipole. From this relation, we can plot what is called the Bode plot. So that's the magnitude of the impedance, which we can rescale using the geometrical factors, which are the electrode area and the effective width of the capacitor, which is this distance between the dielectric dividing surface. And we see, for example, at high frequency, a peak that corresponds to water libration. And at low frequency, something that depends on the distance between electrodes, which is the Debye mode. And if we look at this characteristic time, which is in fact the integral of the normalized charge autocorrelation function, which you see here in the inset. So extrapolating with the capacitor in series model, the time to a bulk system, the time we get, which is about 9 picoseconds, matches well with the characteristic time in the bulk. So this relation can also be analyzed in the complex plane with a Nyquist plot. So here is the complex impedance in the complex plane for the various interelectrode distances. And what you see here as lines are models which correspond to the equivalent circuit models. And this allows also to make the link with the models used by electrochemists. This was for pure water. We are currently investigating the case with maybe more interesting case with ions in the liquids, but this introduces slower processes which need longer sampling times, and this is work in progress. So in the last few minutes, I will come back to this issue of representing the electronic response in the metal in the case where you have a finite screening length. And I'll be faster, especially because during the poster session, you will have the opportunity to talk with Laura, who will be presenting the poster on this topic. But to be very brief on this topic, so in perfect screening, if you have perfect screening inside the metal, the charge is localized only at the surface. In the case where you have a finite screening length, the charge and potential will decay exponentially within the metal with a characteristic length, which is this Thomas Fermi screening length. And so if you try to introduce that as they do in DFT, you introduce functional for the kinetic energy of the electron gas using the description based on Gaussian charge distribution around each electrode atoms. You make some approximations and end up with a total energy, which has exactly the same form as before. The only change is that the A0 matrix here now has an additional term on the diagonal, which involves the Thomas Fermi screening length and the atomic density. And so you can use exactly the same machinery as before, at no additional computational cost with respect to the ideal metal. So if you look at the charge inside the metal, induced by an ion in vacuum, in the case of perfect metal, you have the charge essentially localized in the first plane and localized around the ion. If you increase the Thomas Fermi length from 0 corresponding to perfect metal to a finite value, you do have some charge within the next atomic planes, and the extent, the lateral extent, also increases. The decrease as a function of the atomic plane index is predicted to be exponential. And if you look at what happens in an empty capacitor at a finite voltage, this is what we find indeed. It's also the case, so here in a linear scale, for the potential inside the electrode. So here you have the potential profile across gold aqueous solution capacitor. You have oscillations at the interface related to the structure of water, but what you see here is exponential decay within the metal. And associated with this finite decay of the potential, you have capacitance, which depends on the Thomas Fermi screening length. So here are results in red from the Thomas Fermi simulations, and in black, the prediction of an equivalent circuit approximation, where you take the results of a perfect metal and then combine that in series with something that describes the screening inside the metal. Usually people talk about a quantum capacitance, and here is just predicted from the Thomas Fermi screening length. And you see that qualitatively you capture well this decrease of the capacitance with the increasing Thomas Fermi length, but it's not quantitative. And this is because this equivalent circuit neglects the interplay between what happens inside the metal and what happens inside the electrolytes. And without going into the details, this interplay results in has an influence on the orientation of interfacial water, for example, on the dynamics of the charge fluctuations. And the bottom line is that finite Thomas Fermi length reduces the localization of the charge on the metal, and this results in weaker liquid-solid interactions. So in the last few minutes, I'm going to focus briefly on the effect of screening on interfacial free energies, which you can quantify first looking at contact angles for a droplet on a graphite surface, modeling it as an insulator corresponding to an infinite LTF, or a perfect metal, which corresponds to a 0 LTF. And the change in contact angles that you can measure corresponds to a change in interfacial free energy between the liquid and the wall, which is 6 millijoules per square meter, which is about a tenth of the liquid vapor surface tension for water. So it's quite significant. And again, coming back to the statistical mechanics of the fluctuating charges and the constant potential ensemble, we proposed a new thermodynamic integration scheme as a function of the Thomas Fermi length, which relates the change in the free energy when we change the Thomas Fermi length to the localization of the charge within the electrode. So this quantity here is simply the sum of the squares of all the electrode atoms charges. So not the square of the total electrode charge, but the sum of the squares. And this prediction for the change in the free energy with respect to the perfect metal is shown here. And the red line here is a fit based on a model that is discussed in more detail in the paper, but you see that the extrapolated value is in good agreement with the estimate for contact angles. And this will be my last slide on results. This link with the charge localization, we could explore using a model for the charge distribution. And the charge can be decomposed in an average term, which changes quadratically with voltage and involves the integral capacitance, and another term which comes from the charge fluctuations. This is why it involves the thermal energy KBT, the differential capacitance and how it depends on the Thomas Fermi length, and also a correlation area, this S core here, which is illustrated here. So you have, for a given configuration of the electrolytes, two charge distributions corresponding to a zero LTF or a finite LTF, and you see that the screening length inside the metal changes a lot how the charge is distributed. And this in turn affects the interfacial thermodynamics, and especially it depends on the Thomas Fermi length versus the distance between planes and the correlation length inside the liquid. The distance between plane also enters in the expression here, but I'm not going to describe that in detail. So as a conclusion, I've shown you some examples of what classical molecular simulations can bring to the understanding of these electrode-electrolyte interfaces and the benefit of working out the statistical mechanics of the constant potential ensemble. I've also illustrated how we can tune easily the metallic character of the electrode in this simple model for the electrodes. And if you're interested to know more, there are two complementary reviews, one on planar electrode-electrolyte interfaces, and the other one focusing on the porous electrodes for electrochemical double layer capacitors applications. I didn't take the time to describe that, but I couldn't cover everything. But it's also possible to describe self-consistently the charge distribution and the polarization within the electrolyte if you have polarizable electrolytes. It's not possible at this stage to describe completely chemical reactivity, but there is one contribution to redox reactions that can be efficiently sampled in this simulation, which is a contribution of the solvent polarization around the solutes, which are important to redox reactions, so electron transfer. This is the essence of Marcus' theory. And these molecular simulations can also serve as reference towards accurate implicit solvent molecular descriptions, in particular molecular density functional theory. These are two papers from my colleague Guillaume Jean-Méret in the Phoenix lab. And finally, there are, of course, very important challenges for the classical MD of these simulations, and in particular, obviously, the chemical reactivity. Beyond this solvent contribution to redox reactions, there are interesting developments in that directions. Another issue is the flexibility of the electrodes, which may play an important role. And as a last, but I think very exciting example is the coupling between electronic excitations in the metal and how they couple to the charge dynamics in the liquid. And this has been the focus of two recent studies, and more are ongoing, on the friction of water on carbon surfaces. And I think we will have, during the poster sessions, the occasion to know more, because one of the authors of this work will be present. So with that, I would like to thank again all my collaborators. Just to mention that part of this work is done in our ERC project, and there are two postdoc positions that are still open just for a few days. So if you're interested, not on this topic, but on related topics, get in touch quickly with me. The codes that we use is available at the following link. And with that, I would like to thank you for your attention.
Well, thank you, Benjamin, for this really interesting talk and for providing us with such a comprehensive overview of what you can achieve with classical molecular dynamics simulations in this rapidly developing field. So we have Harinder, who is ready to ask questions. I would invite the other participants who may want to ask questions to Benjamin to just let me know that by typing that in the Q&A tool, and then they will be invited to unmute when their turn comes. So Harinder, you have the mic.
Thank you for the great talk. I learned a lot of things from this. So I have recently started working these constant potential simulations. So one of the questions which I wanted to ask was about the polarizable force fields, which you addressed in your conclusion slide. But is it safe to assume that the electrolytes are not decomposing if we are applying the potential within the electrochemical stability window?
So thank you for your question. So maybe briefly on the polarizable electrolyte case. It's actually a very interesting point from theoretical point of view, and in practice, there are different ways of dealing simultaneously with the polarization of the electrolyte and the fluctuating charges. You can do self-consistent determination of both either iteratively or at once. And there is a recent JChem Fizz paper if you're interested to learn more about knowing more about that. Coming back to the points on decomposition of the electrolyte. So indeed, with rigid models, for example, and non-reactive force fields, clearly you can apply any voltage you want, and this is not realistic. And so it's up to you as a scientist to choose a simulation setup which either corresponds to experimental conditions or corresponds to non-realistic conditions, but then it has to be understood as a systematic study of the parameter of interest. There was also the issue of temperature, for example, when I mentioned the sudden rise in temperature for the constant charge simulations. If you're not careful, you can reach conditions which are completely irrelevant. And of course, ionic liquid would not sustain such high temperatures. I don't know if that answered your point. Maybe one additional point about voltages is that I've mentioned the response I've mentioned the average charge as a function of voltage. I've also mentioned the response to the linear response formula. Differential capacitance predicts the derivative with respect to voltage. But if you consider high voltages, the response is not necessarily linear. You could see an example with the room temperature ionic liquids graphite electrolytes. So dealing with high voltages, you can do this by applying large voltages, but what large voltage means depends on the system of interest.
So thank you for the answer. So regarding this temperature fluctuation, I also wanted to ask that how is it justified to do constant temperature simulations such as NVT when we have these high potentials in our system? So in case of potential temperature range, is it justified to use these constant temperature simulations?
So typically the experiments are also done at constant temperature. And then there might be the question of whether the thermostating scheme in your numerical simulation is relevant, and this time constant of your thermostat relevant. And again, it depends on the system of interest and how large the voltage is. So it depends on whether basically the system has the possibility to dissipate heat sufficiently fast, or whether the thermostat you are using is doing it too fast compared to what the system actually does.
Okay, thank you, Benjamin. Harinder, I see that you have another question in the Q&A, but if you don't mind, we can move to ICP, who has a question, and then we can cycle back to you a bit later on.
Yes, okay. Hi, Benjamin. This is Christian Holm from Stuttgart. Like to ask you a question about your constant potential ensemble and the constant charge. Let's suppose I have a structureless wall and I would simulate, let's say, a primitive model at constant charge, and then corresponding to that simulation at the same average constant voltage. Would you expect in the thermodynamic sense a different distribution of ions, or would you get the same result?
So thank you, Christian, for joining and for your question. So if in a 1D picture, you could expect from Gauss theorem that you would get the same answer. if you have the possibility to polarize the metal, and especially if you have, so maybe I can come back to the charge distribution, for example, here. So the charge distribution inside the metal depends in principle on the electrolyte configuration and on the lateral ordering of the electrolyte. Maybe this is also visible in here. So you see that the induced charge in the metal basically reflects the microscopic configuration of the ions. So the red regions here are basically located where the anions are. And so in a constant charge picture, this would be homogeneous. And in terms of structure, at low voltage, it would probably not change much in terms of 1D structure or even in-plane structure, because it will be dominated by the ion-ion interactions. But if you look at the consequences, for example, on the interfacial free energy, and that was what I tried to illustrate for the case with a finite Thomas Fermi length. So the interfacial free energy is actually quite dependent on this lateral charge distribution inside the metal. And so probably the interfacial thermodynamics, which is also related to the capacitance, will depend on whether you're allowing the charge distribution inside the metal to react to the configuration of the electrolyte. I don't know if that answers your question.
Yeah, I'm not quite sure. I mean, in the constant potential simulation, you also allow charges to fluctuate on certain areas, right?
Yes.
On certain positions. And so if you would, I don't know, decorate that with a constant charge in a similar way,
okay.
I mean, why should be the thermodynamics? I mean, I can see in the fluctuational sense, the dynamics can be different because the reaction is different, but in the constant charge.
So maybe I did not understand. So you're thinking about patches of charges that correspond to.
I mean, just if you realize the constant voltage, I mean, is realized by the induced charges which are living somewhere. And if you would decorate now your plate with a constant charge where you don't allow the charge to fluctuate, wouldn't you? I mean, I would expect that I would get actually the same structure of the electrolyte back, and I would not see any difference.
So if I understand correctly, you're going to freeze the charge distribution, which is not homogeneous. It would look like one of the snapshots here. So in that case, you are really templating the structure of the electrolyte by the charge distribution inside the metal. So probably the configurations that the electrolyte will explore will be strongly biased toward configurations corresponding to the charge distribution. Whereas in the constant potential, you would explore basically all possible configurations that are compatible with the constant potential constraint. I don't know if that makes sense.
Hi, Slavko is here. Hi, Benjamin. Thanks for a nice talk. I wanted to ask a similar question, but if you go to this CDC electrodes with your GBC letters paper, I think from 2013, and on the left-hand side you had a snapshot. Yeah, this one. And I see when you apply the potential, there is the empty cycle. You saw there was a red cycle. It's empty. There are no ions. But when you apply the constant charge, there are some ions inside. And I was wondering if if you simulate longer than for constant potential, will you get ions there? I mean,
sure.
Are you comparing the same equilibrium configuration? So if you simulate in infinity, then I mean, sufficiently long, will you get the same configuration?
So this is really to illustrate the short time dynamics, the transient regime. So eventually you might have ions that go there. It's just that the mechanism which will drive the ions towards that region is not the same. So here, basically, initially, if you impose the charges, then you are inducing an electric field that will drive the ions. Whereas in the constant potential picture, the charge builds up on the electrode as the ions come to polarize and compensate the charge. So the dynamics is then more diffusive in that case.
I understand, but are the final configurations the same? When you apply constant potential, you also have image forces, and that will, I would expect, the higher ion density inside the pores as compared to constant charge potential simulation. So I think even a final configuration will be different for constant charge, constant potential simulations.
They can indeed be different, especially for the reasons we were just discussing with Christian. So if the charge is fixed, then you are somehow templating the wall for particular configurations of the ions, and the configurations might be different, especially so in the nanoporous carbon.
Okay, thank you.
Thank you.
Okay, thank you. We have a question from Paola Carbone.
Yes. Hi, Benjamin. Hi, it's Paola. Thank you very much for the interesting talk. I just have a question about the simulation setup. So in your simulation, do you allow only the charges of the atoms of the first layer of the electrode to fluctuate, or all the charges, so all the charges of all the atoms within the electrode slab or pores?
Thank you. That's a very important point. Thank you for raising this. I'm going to illustrate that with a discussion of screening. So all the electrode atoms have fluctuating charges. In practice, the ones that do have a significant charge that depends a lot on the screening length. So for a perfect metal with LTF equals 0, I don't know if you can see. Oops, sorry. If you can see the pointer.
No.
I'll get back to that. Yeah,
Yes.
so here you see that LTF equals 0 on graphite, for example, most of the charge is localized in the first plane. And then the residual charge is localized in second. And then even though they have fluctuating charges, the other planes have a 0. I mean, the atoms in the other planes have a 0 charge. It's not the case for the finite LTF here. So you see a bit of color there. It decays exponentially within the electrode. So here it's illustrated for an empty capacitor with a 1 volt difference between the electrodes, and you see that there is a color gradient, which also indicates the decay of the charge within the metal. The reason why we had many planes in that particular case is that we wanted to investigate systematically the effect of the Thomas Fermi length. If the Thomas Fermi length is rather small, then we know that just a few planes will be sufficient. And in practice, we don't use that many planes.
Mm-hmm. Then, if I may, just a very quick question. So, how do you decide how wide is the Gaussian? So, what is the parameter, the input parameter in your simulation in terms of how much this charge can fluctuate, and where do you take those parameters from?
Okay, so that's a very good question also. Actually, the value we used for a long time came from the original paper by Ilya Sikman and Michiel Sprik, which was in fact parameterized for platinum. And when we started working on carbon, because we didn't have the possibility to parameterize it in a more clever way, we used that value, which was probably the simplest, but not the most obvious thing to do. And this parameter, in fact, has a big influence on the response of the electrodes. So recently, we tried, this is the work of Alessandra Serva, there is a JChem Phys paper, also with Laura and Mathieu. So discussing the effect of tuning this Gaussian width And in fact, so for the same model of gold electrodes, here not changing the geometry, but simply tuning the width of this Gaussian, and it changes quite a lot the capacitance of the interface, and it also changes how ions adsorb on the surface. So in principle, this is another way of tuning the metallicity. And in principle, it would be good to parameterize that in ab initio calculations.
Yeah, ab initio, right? EFT,
Yeah.
like, yeah. All right, thank you.
Okay, thank you, Paola, also for asking explicitly the last question that Harinder had wanted to ask. So we have two more questions, Guido and then Hernane. I am sorry to do this, but in the interest of time, I would ask you to stop here. So Guido first and then Hernane, and then we move to the first talk by our junior contributors.
Yeah, hi, this is Guido Rao speaking from Milano. I had the same question as Paola, more or less, so, but I have a backup one. So about, for example, the metals, I mean, are they flexible in any way, and or are they just perfectly rigid? And how does it impact also, for example, for setting the density or coupling to a barostat?
Thank you. That's also a good question. So far, all the simulation I've shown are for rigid electrodes, and this the issue of flexibility can be important, especially for the nanoporous electrodes. I mean, this could be an important aspect that has been neglected so far, and it's still possible to do constant pressure or normal pressure simulations by moving the electrodes as rigid objects, as pistons. This is actually something we do to equilibrate the system, to find the equilibrium distance between electrodes at a given pressure, typically normal pressure. And once we have found the equilibrium distance, we switch to NVT simulations.
Okay, and when the metals are rigid and you have this sort of ideal situation where Thomas Fermi length is 0, I mean, all metals are identical at that point, or is still something
there are differences in the, for example, you could tune the width of the Gaussian distribution, which play a role. You can also change the structure, the atomic structure. So for example, graphite and gold have different lattices, and also the non-electrostatic interactions play a role. So typically,
are they Lennard-Jones or?
Sorry?
Are they Lennard-Jones?
Yeah, it's typically Lennard-Jones, except in the case of platinum, where they used from the early simulations. They also introduced, sorry, I'm trying to switch between slides, but it's not working anymore. They also used a three-body term, which was necessary to put, I don't know what's happening with my computer, where they tried to, they had to include that term to make sure that the water molecules would go on the top sides as they should.
Thank you.
Okay, let's move to the last question. Hernane.
Yes. Hi, Benjamin. I am Hernani from Barcelona, RMIT and ICM2. So I have a very quick question. So what is the computational cost introduced by this charge fluctuation scheme in the molecular dynamics?
I'm sorry, I didn't get your question.
What is the computational cost involved?
Oh, the computational cost. Okay, compared to simulations where the charge don't fluctuate, typically now it's only a factor of 2, I would say.
Okay.
So not orders of magnitude. It could be a few more times, but that's the order of magnitude.
Okay, thank you.
Okay, so thank you very much, Benjamin, and thank you all for asking such interesting questions to further the discussion. This is a bad CCAM habit. We lose track of time when we're involved in interesting discussions, but we're now ready to move to the first presentation from our younger contributors. The first speaker is Mui Weng from EPFL, who will discuss for us first principles barrier simulation with implicit solvation model and electrochemical potential. So Benjamin, if you stop sharing, we can have Mui.
Actually, my computer seems to be stuck, so if you could force the function to stop sharing, that could help.
Very good.
Yes,
it's done. So please, Mui, share your screen and start the presentation. Thank you.
Okay, I hope you can see my screen. And my name is Moi Weng from Nicolas Mazer's group in EPFL, and I'm now in my first year of my postdoc here. And my topic today is about the first principle barrier simulation with implicit solvent model and electrochemical potential. And to begin with, I would like to show some background about the electrostatic potential of a solid-liquid interface. So for first principle simulation, this is kind of sophisticated because we have a dipole inside the solid, and we have the molecular or ions absorbed on the solid surface, and we have the solvent molecules with dipoles on near the surface in liquid, and also we have some balanced charge in liquid. So the electrostatic potential changes a lot with all the effect, and and we also have electrochemical potential when we want to simulate some diffusion or chemical reactions. So in my talk today, I want to first show some continuum model on solid-liquid interface, and also the other part is the second part is about the barrier calculations with the normal NEB, and also a famous exploration method for barrier with constant potentials. And for the last part, we want to drive some formulas for the force calculation with constant potential, and to see how the NEB should perform with constant potential. And at last, a very simple example of NEB calculation with constant potential one. So for the first part, we want to show the implicit solvent model. This is a model used to this is a kind of model that used widely in DFT calculation, which do not take the moleculars in liquid into our calculation, because if we use a dielectric number in different place with respect to as a function of charge density on solute, we can save a lot of computational time for the DFT calculation. And in this model, we change the standard Poisson equation to this generalized Poisson equation. And for the charge density less than the minimum charge density threshold, we can consider that area as a water region with the dielectric constant equals to 78, and for the area with the charge density larger than the threshold of the maximum charge density, we consider that part with the solid atoms, and for those parts we have dielectric constant to be equal to 1, and in the middle we have a continuum model to simulate to build a dielectric constant number with respect to the charge density. And for this SCCS model, we also have two terms to change the total energy to fit the solvation energy of the experimental result. We have the first one acted as the function of the surface tension, and the second one as the pressure. And by fit these 4 parameters to the experimental surface energy, we can have a small arrow with more than 200 neutral systems. So also we can see that for some system, the surface energy agrees well with experiment, and for example, for the aminase, this group of moleculars, the surface energy is not that good, but again, we have parameters to tune this surface energy for the DFT calculations. And also we also want to consider the electrolyte in our simulation. So we based on the generalized Poisson equation, we have a Poisson-Boltzmann equation, which has another term with the ionic charge density here. And this ionic charge density follows the Boltzmann distribution. So this function is called Poisson-Boltzmann equation, and by using this Poisson-Boltzmann equation, we can change the charge of the solid surface, and the electrochemical potential can also change with respect to the charge on the surface atom. And also based on the relationship between the potential and the charge on the surface, we can calculate the capacitance, and by using this model, we can have a good agreement with the experimental result on this capacitance. And for the grand canonical DFT calculations, we want the electrochemical potential to be fixed, and the number of electrons can be changed during these calculations. So for this free energy, if we want to minimize this free energy, we want this free energy do not change with respect to the number of electrons. So by doing this formula, we can have the result that the partial total energy of DFT calculation over the partial number of electrons should be equal to the absolute potential, which can be set by users or as an input. So we, thanks for the Janick theory, we have the Fermi energy here. So in grand canonical DFT calculations, the goal is to set the Fermi energy equals to an input number of the absolute potential. Then grand canonical DFT calculation can be performed. And for example, in this paper, the shapes for potential nanoparticles can be predicted as a function of the chemical potential and the pH. For the self-consistent loop, we want DFT calculation can simulate the grand canonical potential in a self-consistent way. So people can change the basic pooling mixing in DFT self-consistent loop. With the normal pooling mixing method, people can change it to a grand canonical way, which during each step between the self-consistent, the number of electrons can be changed, and the target potential, chemical potential can be achieved after several loops of self-consistent calculation in DFT. And so after the solid-liquid interface, we want to focus on the barrier calculations. And this is NEB is one of the most famous barrier calculation method. And for this method, so for the normal NEB calculations, different from the traditional drag method. People can have different chemical reaction direction to be set and to find a barrier in these NEB calculations. And for what we want to do in grand canonical DFT, so for NEB and for the relationship between NEB and the DFT calculations, we want to input a force that is calculated by DFT, and then NEB can find the saddle point by its by minimize this NEB force, and then a transition path can be achieved. And so for there's also a well-known way to calculate the barrier in electrochemical potential, which is called the extrapolation method. So for this method, as we can see, with the atom move, this is an example of two hydrogen atoms combining into a hydrogen molecule. And in this reaction, the work function of the whole system will change, and also the barrier will also change with the chemical reaction happens with different images. So in this extrapolation method, people can use supercells to predict how the so if we can imagine there is a infinite large solid and liquid interface, and there's only one atom move from the solid surface to the liquid, so the surface charge of this system changes very little, so the potential of the whole system will not change. By using this this way, to people can first use small unit cell to calculate activation energy and also the reaction energy of the barrier, and then people can use a larger supercell, and the people can plot the changes in energy with respect to the changes in potential, and with this point cross the y-axis, then people will get the reaction energy with zero change of the electrochemical potential, which is also a constant potential calculation. But we want to do, if we want to do the grand canonical way just in DFT with one short calculation, and also for the calculations that if a lot of some large changes in the surface, so the electron structures will change when the number of electron changes. So we will try to use a grand canonical way to do the self-consistent loop to solve the basic DFT result and combine it with NEB calculations. So with the forces in grand canonical ensemble in DFT, we will try to drive how the force will react as when we perform a constant potential calculation. So for this grand canonical total energy, we will define the total energy as the standard DFT calculation energy plus a number of electrons multiplied the absolute potential. This alpha indicates the atomic structure, and this is the number of electrons and the Fermi energy. So as we can imagine, if the number of electrons changes in the system, the total energy will also change. So we define this with additional term with the number of electrons multiplied the absolute potential. So for the ground canonical force, by definition, we will have two structures, which is alpha 1 and alpha 2. And for these two structures, we have two different number of electrons, which is Ne1 and Ne2. And so the ground canonical force can be defined in this way. And if we combine these two equations here, we can use the total energy of standard DFT to express this ground canonical force. And thanks to the Jennings theorem and the definition of the standard DFT force, we can see that the second term and the third term on the ground canonical force is the left-hand side of the Jennings theorem, and the last term is the right-hand side of this equation. So if this indicates that if we have our Fermi energy to be fixed to the position where the absolute potential is, we will have the ground canonical force equals to the standard DFT calculation force. So we can perform a ground canonical DFT simulation with the number of electron changes and with a setting electrochemical potential. And we can solve the atomic force by a standard Hammond-Feynman theory in DFT calculations. And so if we have a force for the ground canonical DFT, then we can first deal with the solid-liquid interface with the implicit solvent model and Poisson-Boltzmann equation, and then solve the constant potential problem with the ground canonical self-consistent polymixing algorithm in quantum espresso. And we can then use a constant potential Hammond-Feynman theory to calculate the atomic force and then do the barrier calculation in NEB. And the last, this is a simple toy example of lithium iron moved on a graphene layer. So during the calculation, we fixed all the carbon atoms, and there's only, as we can see, if the lithium atom moves from one point to the other point, from the start point to the end, the lithium atom will move in Z direction, and the work function will change. So if we see here in the x-axis is NEB image, and the y is the work function here, we have the work function changes respect to the lithium atom moves, and we have an energy barrier. And also, if we want to do a constant potential NEB calculation, we have so the number of electron changes, but this is a very simple example, so that the number of electron changes very little, and the potential keeps the same number in all the calculations. And also, we want to say that the total energy defined here is the standard DFT energy plus the number of electrons multiplied by the absolute potential. So in conclusion, by using the implicit solvent model and the Poisson-Boltzmann equation, we can simulate the surface capacity on a solid-liquid interface. And with this continuum model and the ground canonical self-consistent DFT, we can do a constant potential calculation, and also with combining with NEB calculation, this barrier can be calculated in a constant potential form. So I would like to thank my group and the NCCR catalysis to fund this research. And thank you for this chance to sharing my research here. Thank you for your watching, and happy to discuss.
Thank you, Mui. Thank you very much for this nice talk. As we wait for members of the audience to signal their intention to ask questions via the Q&A tool, maybe I can start by asking one myself. So you mentioned that you're using MEB to compute barriers. These are energy barriers?
Yeah, energy barriers, yes.
Do you think that it would be interesting to explore, free energy landscapes in association with this type of problem?
Yes, I think the yes, free energy is more related to the experimental result, and but yes, for now, I think the thing I'm doing now is to find whether the constant potential and the constant number of electrons will have different transition state, or where they have much difference between two methods.
Okay, thank you. So any more questions? Benjamin has a question. Go.
Thank you for the nice talk. I was wondering, since you mentioned finite size effects with the extrapolation method, if you also considered the effect of the finite lateral side in the ground canonical case.
I think this is you mean this extrapolation method in?
Yes. So there is an effect on of the finite lateral size. And I was wondering, in your study with the method you propose, if you also investigated the effect of the lateral size.
So for example, in our really simple example here, the supercell here, I think what matters here is the if we have image interaction with the lithium atoms, because if we change the number of electrons of the system here, the Poisson-Boltzmann will keep the potential to be a constant number. So different sides of the supercell will not affect the potential, but only maybe the image interaction between these lithium atoms, I guess. Yeah.
Thank you.
Okay, maybe we can move to one last quick question by Xue Ping.
Hi, Moi. Thanks for the nice talk. I also have a question on the case study of the lithium diffusion on the graphene. In next slides, you show its constant potential. But I see there's no difference in the barrier when you use the constant potential, constant charge. And also I'm wondering what is the potential here you put when you calculate barriers?
Okay, so yeah, this is a really a thing that we found, that these two barriers have almost the same number. I think one thing is that because the number of electrons changes very little, and there's no much effect, because first this lithium iron, the moves in z direction changes the work function with maybe just 0.1 eV, and also the base is a graphene, which can change its Fermi energy with very little changes in number of electrons. Yeah, but yeah, you are right. This changes very small in barrier, but we would like to do more tests in more sophisticated system. For example, we can have this metal with this hydrogen combined to each other to see if there are much change between the constant potential and the constant number of electrons.
Okay, so a follow-up question for the constant potential case, show the electron number. Is that what's the electron number means? It's the lithium electron.
The electron number in the whole system. So we
Whole
perform.
system. Yeah. Okay, thanks.
Okay, thank you very much. Thank you, Muri, again for this very nice presentation. And I think we're now ready to move to our second talk by Geoffrey Monet, who will discuss for us unified non-equilibrium simulation methodology for flow through nanoporous carbon membrane. Thank you. The floor is yours.
Well, thank you. I hope you understand. You hear me quite well. Well,
yep.
My name is Geoffrey, and I'm postdoc at CNS Paris in the group of Derek Bocquet. And today I'm going to present you an original non-equilibrium simulation approach, which allows us to fully characterize the flow properties through a new kind of carbon nanomembrane. Well, membranes, as you may know, are really at the center of many technological devices that may have a huge industrial and societal implication. For example, desalination becomes even more important with the increasing water access issue. And today, the major part of desalination is done thanks to reverse osmosis. Reverse osmosis is just sieving seawater under a huge pressure drop across a semi-permeable membrane. This method needs large area of semi-permeable membrane that must be cheap and mechanically robust. But actually, the functionality of membranes cannot be summarized to filtration alone. Indeed, I could talk about, for example, osmotic, the harvest of osmotic energy, which we call the blue energy, from a salt gradient, like the one between fresh and seawater. Well, all of this requires membranes with even more advanced properties. So in this context, I'm going to present you a new generation of membrane only made of carbon nanomembranes, also called CNM. Well, the best way to explain you what are CNM is to explain how to build them. So first, you have TPT carbon chains that are grown on a gold foil. So you will end up with like a carpet made of hairs, where each hairs are TPT molecules. Then you place this layer under an electron beam in vacuum. And because of the radiation of electrons, there will be a reorganization of the interatomic bonds. And because TPT chain will actually cross-link between each other. And finally, we just remove the gold foil, and you end up with a self-assembled monolayer that is just self-supporting. Okay, and the thickness of this membrane is given by the length of TPT molecules, which is around 1 nanometer. If you put this layer under an STM, for example, you will see that this membrane shows a very, very high porosity with pore whose diameter is less than 1 nanometer, which is very tiny. But the thing which is very interesting here is the fact that these membranes are mechanically robust, and we can already produce them in the range of centimeter. You have to know that this is something that we are not at all capable to do with membranes based on carbon nanotubes, for example. The upscale is always an issue for this kind of membrane. In this figure, you can see that with their extremely high porosity, carbon nanomembranes have a very high permeability to water compared to other membrane based, for example, on porous graphene or carbon nanotubes. Yet with their diameter of less than 1 nanometer, they have almost perfect ion selectivity. So basically, this membrane seems to be the ideal candidate for desalination because they have a huge permeability for water. They are impermeable to salts, and they can be already designed at large scale. Well, given this promising feature of CNM, a future and emergent technology project have been founded by Europe. This collaboration brings together several teams at European level, and most of them are working actually on the design and the improvement of the membrane itself. At TNS, well, we made some experiment as well, but we also try to pave the way for new design or further experimental measure by providing a theoretical description of what happened at the nanoscale by answering the following question: what is the properties of confined liquid transport through CNM under an external stimuli like pressure drop, chemical potential, or voltage drop? So to answer this question, the first step is to define a well-controlled system to make the math or simulation. For this, I actually base myself on 3 facts. First, the measurement that come from STM. Okay, we saw that those pores are cylindrical-like shape. Okay. Then we also compute some ab initio simulation to check if the structure is stable, if a pore made only of TPT molecule is stable, and it is the case, so good news. And finally, I take inspiration from how we actually describe the structure of carbon nanotube from the rolling up of a graphene sheet to at the end propose a very simple and regular model for the nanopore, because a nanopore will be of the CNM will be seen as a rolling up of this layer made of TPT molecules that are cross-linked to each other. So the length of this nanopore will be fixed, given by the length of TPT molecules, which is around 1 nanometer, as I said previously, and the range of the radius will be between 0.5 to 0.0 nanometer. Okay, depending on the number of anti-TPT molecules that you align in the layer. Then we will perform classical molecular dynamics simulation. So our system is simple. It is the following. So first, we will consider a nanopore of a given radius. We will add some walls on both sides of the nanopore to ensure the sealing of the system. Then we place a reservoir of water molecules whose density is as close as possible to the density of bulk water. And finally, we add some chloride ions, okay, chloride and sodium ion at 1 mole per liter. So the reservoir you see here is the system is periodic along the three direction of space. So the reservoir is replicated on both sides of the membrane. There is only one reservoir here. And about the configuration of molecular dynamics simulation is very classical, so I will not talk a lot about that. Water molecular SPC, carbon atoms are fixed in space, and everything is computed on GPU with GROMACS. Okay. The first things to try with this setup is to apply a pressure drop, like in experiment. There are typically 2 approaches to this for doing this. One can consider a 2-tank system. Okay, this is a classical way to do this with 2 tanks with different conditions, with different pressure, for example. Unfortunately, if you do that, you have to simulate 2 reservoirs, so it is 2 times heavier, and the simulation will be limited in time. There will be no steady states. The system will never reach a steady state, since one reservoir will just fill up another one. So we choose another approach, is to consider only one reservoir and to define actually a control slab here in blue, in which we will apply an external force field to all particles that belongs to this slab. Okay, so if we do that, you will end up with a pressure profile that will look like this, and you can connect this pressure drop to the individual force you apply on each particle. Okay, it's just a force balance, and by doing that, you keep the periodicity of the system, and you can reach a steady state. Okay, the particle will just flow under this pressure drop. Okay, so you can accumulate statistics over long time. So now let's count the number of particles that flow through the membrane. For example, in this figure, you can see the number of water molecules that pass through the nanopore under the pressure difference of 10 megapascal. Then we can compute actually the volumic flux. Okay, so by computing the volumic flux, we can gather the flux for water and ions on the same figures. And qualitatively, we see two things. First, there is a difference in volumic flux between water and ions. And there is also a difference between chloride and sodium ions, which means that there will be a non-zero ionic current. But I will talk about that a little bit further after. And as you can see, well, the volumic flux, of course, increase with the radius of the nanopore, but it follow a Power law where the power is equal to 3. Okay. And to provide actually a more quantitative interpretation of these results, we propose to model the molecular flow of water and ions with a very simple homogeneous model. Okay, so actually the fluid, the water fluid and ion and sodium will be modeled as an homogeneous cylinder whose radius is equal to the radius of the nanopore minus the depletion length. The depletion length is the characteristic distance between the particle and the nanopore wall, and it is defined well with this formula. And to compute it, we just perform a molecular dynamic simulation at equilibrium. We measure the molecular density profile, and we use this formula to compute the depletion length, and we found this value. Well, with the help of this model, we can, for example, understand how water flow are generated under a pressure drop. Indeed, for a water molecule to pass through the nanopore, it must first be able to pass from the reservoir into the nanopore. This will create a certain resistance, which is called the entrance effect. And then you have the inner friction of the water molecule on the wall of the nanopore. So we get the famous Poisson profile, where here B is the slip length, and it can be non-zero. And like an electrical circuit, we just sum up these two resistance to get the permeability factor. At the top of the slide, you have the expression of both terms. In order to compare them, we will have to determine the slip length. Right? And to do so, as it is commonly done for carbon nanotubes, for example, I consider an infinite nanopore without any reservoir, okay, like this. And I apply a certain force F to the water molecule, and I just wait that those molecules reach their terminal speed, okay, at steady state, and I measure the friction coefficient, which can be related to slip length. Well, to make long story short, we end up with a slip length that is more than 20 nanometer. This is huge compared to the radius, the pore radius. But it is not unexpected, because it is a value that is typically found in carbon nanotubes. So in the end, we can say that the friction factor is negligible compared to the entrance effect. Actually, the friction would have to be 10 times higher to have a significant impact on the permeability. We can forget what happens inside the nanopore. What is important is the apparent cross-section of the nanopore. So here is what it looks like in this figure. Okay. The red curve is the theoretical model, considering only the entrance effect. The purple and green curve are the theoretical curve for sodium and chloride ions. And we get those curves just by assuming that ions are actually passive particles that are carried out by the water flow. So the speed of ion will be just equal to the speed of water molecule. And we can rewrite this relation in terms of volumic flow. But when we do that, we just have to take into account the fact that the cross-section area accessible by the ions is not the same as that of the water molecules, since their depletion length is not the same. And as you can see, the agreement is very good, which means that with a very simple homogeneous fluid model, we have managed to capture a large part of flow properties, which is at molecular scale here, because the nanopore is less than 1 nanometer. And here I insist on the fact that there are no fitting parameters in this model. We just measure the depletion lengths in other simulation apart from those out of equilibrium simulation, and then we put every figures in the model. Actually, in nanofluidic, we prefer to work with these quantities rather than volumic flow, where J is the excess ionic molecular flux and IE just the ionic current. Why? Well, because they are thermodynamic quantities, which is conjugated to thermodynamic driving force that we can apply experimentally. Indeed, experimentally, we can apply a pressure drop, but we can also apply a chemical potential drop, which is a different concentration in reservoir. Or we can apply an electrical potential drop. Thus, we can write the thermodynamic flux as a linear response of thermodynamic driving potential, and we end up with the transport matrix. And something which is very interesting is that the transport matrix has the fundamental property of being symmetric. Thus, for example, it is expected that the electroosmosis flow, which is the water flow caused by an electrical potential drop, is equal to the streaming current, which is the electric current generated by a pressure drop. Okay. So to access all of these coefficients of the transport matrix, I will actually generalize the approach we use to apply a pressure drop. For example, to apply a chemical potential drop, we will apply a force field to all particles that belongs to this green slab, in order to push the ions in a side of the reservoir, and to generate a difference of concentration. And we can relate, as before, we can relate the individual force to the chemical potential drop. Okay, and we can do the same for the electrical potential drop. We just put some electric field in this lab, and we end up with more positive ions in one side of the reservoir and more negative ions in the other side. So here you see that we have a unified approach, and thanks to this unified approach, we have been able to compute the full transport matrix, which is the linear response of the non-equilibrium system under the effect of those different potential drop. I will not go into detail of all of these results because it will be too long. However, we see that the matrix is symmetric. This is very important and shows that our unified approach is self-consistent. Okay. We also see that there is a good agreement between simulated results and our very simple model based on homogeneous fluid. Well, I haven't talked about this yet, but the permeability and the conductance values are in good agreement with experiment, which is important as well. And finally, even if the pore is not charged, it is neutral, we see that the off-diagonal terms are not zero. Okay, and these things, for example, may open up to very interesting perspectives, such as for harvesting osmotic energy. Indeed, we can estimate the maximum osmotic power that can be recovered between river water and seawater. The power is just equal to that, and the current is just generated by here diffuse osmosis. We can take its symmetric terms, on which we have more statistics as well. So that's why it's interesting to have a symmetric transport matrix. We do the math by taking the right panel, and we end up with this curve. Here you have the extrapolated osmotic power that increase with the radius of the nanopore and reach considerable value with in the round of megawatt per square meter. This is very huge because actually a membrane that produces only 20 watts per meter square is already a very good membrane for for blue energy. Here, of course, when we stack nanopore, this performance will be reduced. But it shows that carbon nanomembranes may offer a unique avenue as membrane for osmotic energy harvesting. So in conclusion, I will just summarize what I said. So we saw together that we developed a new approach to perform non-equilibrium molecular dynamics simulation under the effect of pressure, chemical potential, and electrical potential drop, while maintaining the system in steady state. And thanks to this approach, we found back the exceptional permeability properties of carbon nanomembrane, and we saw that the permeability is actually mainly limited by entrance effect. And thanks to this approach, we find the first complete description of the transport properties through such a system. And thanks to that, we could design new generation of membrane that are optimized for other things than just filtration. And for example, carbon nanomembrane may have a huge potential for osmotic current. Okay, so I would like to thank my supervisor, colleagues, and co-author of the paper that is associated with this study, that you can already find it on arXiv. And I invite you to take a look at the latest paper of the Micromegas team, which is quite fascinating. It talks about, for example, quantum friction of water and graphene. So it's quite a program. Well, thank you for your attention and your watching.
Thank you, Geoffrey, for this very nice talk. So we do have a question from the audience. Guido, you're on.
Nice talk. As usual in this non-equilibrium molecular dynamics method, I think it is critical to select the value of the perturbation which gives you linear response. And was it complicated in your case?
That's a very good question, and I was expected to this question actually, as you see. Actually, yes, I had to perform many simulations with different amplitude for those force I put in this simulation, and at the end I found I tried to take the maximum value while keeping the linearity of the response. And for example, for the pressure drop, it is quite common to have a pressure drop in simulations that reach like 200 megapascal and so on, because you see that the flow of water particles stay strangely linear to this very high value of pressure drop. But here, when you take a closer look of what happened for ions, you see that the response become nonlinear at way lower value of pressure drop. So that's why we had to take we have to be very careful of what we're doing here. And here, in my case, I took a pressure drop of 10 megapascal, which is way lower, and actually closer to what we can find in a desalination plant, for example.
Thank you. Nice.
Thank you. We can move to the next question by Stephen Cox.
Yeah, hi, thanks. That was a really interesting talk. My question is, so you have this really large slip length in your simulations, which is coming, well, you have this very smooth like carbon nanotube setup. When you look at the experiments, they look quite sort of rough and they don't look smooth, like just by eye. Is that true? And do you expect it to have a large impact? And would you be able to incorporate? Okay, yeah, great.
Yeah, thank you, Stefan, for your question. Indeed, it was quite a concern the fact that when you look at the real image of the membrane, the pore seems to be quite deformed. Okay. So we check actually the impact of the deformation of the pore by taking a circular pore and by deforming it, either by stretching one hand or the other hand, or even overlies one of the hand. Okay, and at the end, what we found is that the important factor here is the apparent cross-section area, okay, the minimal cross-section area. Because if you take the minimal cross-section area and you take an analog perfectly circular nanopore with the same area, you will find the same permeability, okay? So and actually the pore is quite short, so you cannot have a very large deformation inside the pore.
Right. Okay. Thank you.
Okay, next question by Francois Peters.
Hello, do you hear me?
Yeah.
Yes.
Very nice talk. I had seen your paper already on the archive. So I have two small questions. First, what's the thickness of the experimental pores? So the length. And the second one is, why don't you have any problems with falling?
So for your first question, the thickness of a membrane is equal to the thickness of the TPT molecules, which is 1 nanometer. So here it is the first question. But the second question, I didn't understand what you said at the end. It just foiled.
Yes, falling. So that's that the ions get stuck at the entrance of the pore.
Yeah. Actually, I didn't add any problem on this kind. No, I never saw a problem of ions that are just stuck on the entrance of the nanopore. But yeah, I know that some people have this kind of problem, but in my case, I never saw this problem. So I cannot answer your question clearly.
Thank you.
Okay, thank you. Last question by Paola Carboni.
Yes, thank you very much for the very interesting talk. I have again also a question about the experiments, I'd say. So when you look at this graphene pore channels, for example, the experimentalists always mention that there are definitely OH groups, oxidrylic groups attached everywhere, especially at the edges where the ions or the water is supposed to enter. Do you know if you have similar problems with this membrane?
I know I know what you are talking about graphene, about nanoporous graphene. In our case, we made experimentally we don't know, but we try to make some ab initio DFT simulation to check if it may be oxidized, if there is some oxygen groups on the entrance or exit of the pore, and it may be not, but it's not sure for now. So for now, we just say there is no, but yeah, maybe there is.
Okay, thanks.
Okay, thank you very much. Thank you, Geoffrey, once again for this very nice talk. Before we conclude, I would just like to share again my screen to make sure that you're all aware of the next topic that we will cover in this Mixed Gen series. And this instead is related to data science in biophysics. And we have Zoe Cornia as our experienced speaker from the Academy of Athens. So I hope to see you also there. As it has been mentioned, we do record these sessions, which means that the videos are going to be available on the MixedGen website, on the CCAM website here, but also on the CCAM YouTube channel, to which I invite you to register so that you can always be informed of uploads of new interesting topics and talks. With that, I think we're ready to conclude this first part of this session by thanking you all and thanking our speakers again for presenting such nice talks and promoting a really lively and interactive discussions. Thank you also to the participants for sharing with us their questions. And that's it. For those of you who have registered, we will see you in Gather in a few minutes. Thank you very much.